Hey guys, welcome back to chapter 14. We have been talking about the integrated rate law for a first order reaction. What we're going to do today is look at the integrated rate law for second order and zero order. We're going to kind of combine the two into one so we can move faster now that we understand this idea. So integrated rate law for a second order reaction. We're going to put together this new equation very much the same way that we put together the first order one. So remember, for a second order reaction, we've got this exponent of 2 up here. So that's what tells us that it's a second order reaction. So again, we're going to take the rate law. We're going to take that average rate of the reaction. We're going to combine those two formulas, and then we're going to integrate. So again, this is going to be the calculus portion that you're, of course, not responsible for. But I integrate, I rearrange, and I get the equation, the integrated rate law for a second order equation. Again, we're going to see this equation of a line. So we're going to be able to graph this data. So remember that our equation of a line is y equals mx plus b. So our y in this case is going to be 1 over the concentration of A at time t. Our m is still going to be k, so the slope of our line is still going to be k. We're going to graph this against t, and then our intercept is going to be 1 over the initial concentration. Okay, so similarities in that we've still got this y equals mx plus b. We've integrated. We can recognize this as a second order. Difference is there's no natural log this time. We're using the 1 over the concentration in this case. Okay. So again, here's what a graph would look like. So we're going to graph this data, again, with time on the bottom here on the x-axis. Our y-axis in this case is 1 over the concentration of A. Remember, for the first order, it was natural log. And then the other difference I see here is that when we graph this information, it's a positive slope. That's just how the numbers shake out. There's nothing to that slope being positive versus negative. But just something to note, the k value on the graph would be a positive number. And we see that again here in the equation, that this is a positive k, where the other one had a negative. Okay. So let's take a look at how we can use experimental data to determine the rate of a reaction. So let's say that I did a chemical reaction and I monitored the concentration of NO2 over a given amount of time. So every 50 seconds, I measured the concentration of NO2. So reached in, measured it, 50 seconds go by, measure again, 50 seconds go by, measure again. Okay. Once my reaction is complete, or I stopped taking data, I take this information and I look at it and I say, I'd really like to know what order this reaction is. What kind of reaction is this? First order, second order? I'd like to know that. Well, let me try this. Let me try to graph this time versus the natural log of this concentration. So I'm going to put natural log on the y-axis. I'm going to see how the data shakes out. Well, when I do that, the dots represent my actual data. The red line would represent the line if this was a first order reaction. And what I see is that my data does not fit that line well at all. So if I were to try and see if this was a first order reaction, I would graph this information. I would look at it and say, yeah, that doesn't fit. That doesn't look right. So this must not be a first order reaction. It's got to be a different order. Okay. So I'm like, well, maybe it's a second order reaction. So I'm going to graph it time on the bottom. And over here, I'm going to put in 1 over the concentration of NO2. So 1 over this number, 1 over this number, 1 over this number, so on and so forth. And when I graph that data and then I put a line of best fit on that graph, what I see is the data fits beautifully. So what this tells me is that since I was able to graph it 1 over the concentration of NO2, this must be a second order reaction. So again, the data is telling me what is the order of this reaction. Okay. And again, if you put this into your calculator or your computer, you can say, hey, smart guy, can you spit out a reaction, or excuse me, can you spit out the equation for this line? So y equals mx plus b. So this will give us our K value, right? So the slope of this line is 0.255. And so our K would be 0.255 in this case. So I could ask you a series of questions, just like I did for the first order reactions. So using this equation, I could say the initial concentration was this, K is this, 300 seconds went by. What is the final concentration of A? And then it'd just be some algebraic rearrangement to get to that information. Because there's no natural logs here, I feel like the algebra is a little bit more straightforward, a little bit easier. So I don't do any in the lecture show, but there are some, if you go to the video links and go to Khan Academy or Bozeman Science, there are some examples worked out there if you're struggling with the algebra of it. All right, so lastly, we've got a zero order reaction. So remember, those are the three that we talked about, zero, first, and second order. For a zero order reaction, we're going to do the same thing. We take the rate law, set it equal to the average rate of the reaction, and then we integrate. We do a calculus or apply calculus. And what we see for a zero order reaction is a very, very pretty equation or formula here. So we see that the concentration of A is equal to negative K times T plus the concentration of A at time 0. So no natural logs, no 1/overs. This just gives us the clearest picture of the concentration of A. So we pray for zero order reactions when we're working here, right? And what we see here is a graph we've actually already seen before. So when we take the integrated rate law and we put time on the bottom and we put the concentration of A on the side, again, we see this nice straight line. So this tells us that it's a zero order reaction. And again, the slope of this line is going to be K. Something to point out, this is a negative slope. So that's where this negative in the equation comes from. So that is a negative slope when it spits out K for us. Okay. So here's just a summary slide of everything that we've talked about so far in chapter 14 for the second half of the module. So here's the order of the reaction, 0, 1, and 2. This is the rate law. So this is what we actually talked about in your previous module. This is what you were doing in lab this week. Here's the units for K. So this is particularly helpful now because we don't necessarily solve for K. K is somewhat given to us on a graph. And if we know that it's zero order, we can just plug the units on the end of K. Here's the integrated rate laws. So this is the integrated rate law. This is just a slightly different form of this equation. So this is what spits out when you integrate, and then we rearrange it to look like that. Both are the exact same thing. Here's the graphs. And then the next slide, the next video, we're going to talk about half-lives. And I only talk about half-lives for first order reactions. That's why these two are grayed out. But there's the half-life equation, and we'll talk about that in the next series of slides. Okay. And as I alluded to, this idea of K is very helpful now that we have K essentially being spit out for us or given to us. One thing I like to point out here is so far we've dealt with seconds, but if the problem says 365 minutes go by, then the units for K would be 1/minutes. Or if it says 2,000 hours go by, then it'd be 1/hours. Or 45 days go by, then it'd be 1/days. So these units for K, this time piece can change depending on what the time is in the problem that we're dealing with. So just a little nuance there that I'd like to talk about. For the most part, we talk about seconds, but just keep an eye on that. So I hope you guys found this helpful. Go work a bunch of integrated rate law problems.